Welcome to the deep dive. Today, we're digging into one specific entry in the online encyclopedia of integer sequences. You know, the OEIS.
Ah, yes, the OEIS, an incredible resource, like a massive dictionary, but for number sequences.
Exactly. And for anyone studying number theory, getting comfortable with the OEIS is, well, it's really key, isn't it? It opens up so much.
It truly does.
Mm-hmm.
And the sequence we're tackling today, A000251, is a great case study. It shows how these entries link definitions, history, computation, all in one place.
Absolutely. So our mission today, let's really unpack A000251. What exactly is it counting, why the sequence, and what can we learn just from looking at its OEIS page structure?
We're talking about the number of trees that has a diameter at exactly 6.
Right, trees. Okay, but we should probably clarify not like oak trees or maple trees.
No, not biological trees. In graph theory, a tree is much simpler. Think of points, vertices connected by lines or edges.
Okay.
The crucial things are it's all connected. You can get from any point to any other point, and there are absolutely no cycles, no loops.
So it branches out, but you can never circle back to where you started by a different path.
Precisely. It's the most basic kind of connected graph you can have without any redundant paths.
Got it. And the diameter, what does that mean for a tree?
The diameter is the length of the longest possible path between any two vertices in that tree. You find the 2 points that are farthest apart, and then count the number of edges on the unique path connecting them.
Okay, longest path. So on 000251 is counting the number of different types of trees, structurally different, right?
Yes, non-isomorphic is the term. We don't count mirror images or simple rotations as different.
Right. So the number of non-isomorphic trees where that longest path has exactly 6 edges. Why? Why 6 specifically? What's interesting about counting trees with a fixed diameter like that?
Well, counting combinatorial objects based on their properties is, fundamental.
Right.
For trees, diameter is a key structural property. Fixing it, say at 6, puts a strong constraint on the tree's shape. It means the tree has to be sort of long and thin, in a way. It can't spread out too widely relative to its number of vertices. To even have a diameter of 6, you need at least 7 vertices, right?
Ah, yeah, the 2 endpoints and 5 edges connecting them means 5 intermediate vertices, 7 total.
Exactly. So this sequence, A000251, tells us precisely how many distinct ways you can arrange a given number of vertices, starting from 7, into a tree structure that meets this specific thinness requirement of diameter 6.
That's fascinating. It turns a definition into a concrete counting problem.
Yeah.
Okay, let's look at the OEIS page for A000251. Near the top, it says, formally, M2887N1158. What's that about? Old names.
That's right. It says the sequence has history. M2887 means it was in Neil Sloan's original 1973 Handbook of Integer Sequences.
Wow, the classic.
Indeed. And N11158 is its number, the 1995 expanded version, the Encyclopedia of Integer Sequences, co-authored with Simon Plouffe. So seeing those tells you immediately this isn't some obscure sequence someone just submitted. It's been recognized for decades.
It's got pedigree. Okay, the sequence itself, it starts 1, 3, 11, 29, then 74, 167, 367. They seem to shoot up pretty quickly.
Oh, they do. As you allow more vertices, the number of ways to arrange them into a diameter 6 tree grows very fast.
Is there a simple reason for that rapid growth, like intuitively?
Well, think about building one. You need that central path of length 6. All of their vertices have to hang off that path or off branches coming from it without making a longer path.
Okay.
As you add more vertices, you have more choices about where to attach them near the middle of the main path, near the ends, off existing branches. The number of ways to combine these attachments grows combinatorially. Lots of possibilities open up.
Ah, I see. More building blocks mean way more ways to put them together, even with the diameter 6 rule. Okay, below the numbers it says offset 7, 2. What does that tell us?
The offset is crucial for understanding the indexing. The first number, 7, means the sequence really starts at index N7. So the 7 is the first term listed, corresponding to trees with 7 vertices.
Which makes sense. As we said, you need at least 7 vertices.
Exactly. The second number, 2, tells you which term in the sequence corresponds to the second value of the index for which a term is given on the page. Here, the first term shown is a 7-1, the second is A83. Sometimes sequences might have initial zeros listed, but here A7 is the first meaningful term, and is where the list starts. So AN is the number of trees with n vertices.
Okay, so A71 means there's only one way to make a diameter 6 tree with 7 vertices, which must be just the path itself, right?
Yeah, it's the simple path, P7, then A83 means there are 3 ways with 8 vertices, and so on.
Got it. And non just means non-negative integers.
Yes, standard keyword. They're counts, so they won't be negative.
Now, one really useful bit on these OEIS pages, especially I think for students, is seeing how the numbers are generated. There's a PRA-OG section with pay or I code. We won't dissect the code, but what's its significance?
It shows that finding these terms isn't usually about drawing trees by hand, especially for larger numbers of vertices. It's done using computer algorithms based on deeper mathematical techniques. The comment there mentions the shifted Euler transform. That's a technique from combinatorial enumeration, often connected to something called generating functions.
Generating functions. Can you give us the quick idea of why those are useful here without getting too technical?
Sure. Think of a generating function as a kind of mathematical clothesline where you hang your sequence terms as coefficients of powers of x. For something like trees, you can often figure out the generating functions for simpler tree types, and then use mathematical operations like this Euler transform to combine them or modify them to get the generating function for the more complex thing you want to count, like trees of diameter 6. The Piri code is basically implementing that generating function machinery.
So the code turns theory into actual numbers. It confirms the sequence isn't just guesswork, it's calculated.
Precisely. It stems from rigorous theory. And speaking of theory, look at the references. Beyond the Sloan handbooks, there's a 1960 paper by John Riordan, Enumeration of Trees by Height and Diameter. That sounds important. Oh, it's absolutely foundational. Riordan was a pioneer in combinatorics. That paper laid out many of the core methods for counting trees based on properties like height and diameter. Sequences like A000251 build directly on the theoretical framework he developed.
So the problem itself has deep roots.
Very deep. It's a classic combinatorial problem.
Okay, and then under links, there's this table from Christian Seavers. It lists terms way out to N9286. That's a lot of terms.
It is. And that highlights another key aspect of the OEIS. It's a dynamic living database. People are constantly extending these sequences. Computing terms that far out for tree enumeration is computationally intensive. It requires serious algorithms and computing power.
So people are still actively working on this sequence, pushing the computation.
Absolutely. Seavers' contribution shows ongoing interest and the power of modern computation applied to these classic problems.
And the extensions note says Sean Irvine added terms back in 2010. Plus, the last modified date at the bottom is June 16th, 2025. That's today.
Well, hypothetically today for a recording. But yes, a recent date like that shows the page isn't static. It's actively maintained and updated. Someone might have added a comment, a link, a cross-reference, or maybe even verified a new term. It reflects current knowledge.
It really emphasizes the OEIS as a live resource. And A000251 isn't alone, is it? There are links like index entries for sequences related to trees and the cross-refs.
Right. Those sections place the sequence in context. It's part of a whole family of sequences about counting trees. The cross-references are particularly interesting. They point to directly related sequences.
Like A000550, or what's that one?
That's the sequence for counting trees of diameter 7.
Oh, okay. Makes perfect sense. Study diameter 6, then look at diameter 7.
Exactly. The methods are often related. Comparing A000251, diameter 6, with A000550, diameter 7, lets you see how changing that single parameter, the maximum path length, affects the count. How does adding one more edge to the allowed diameter change the possibilities? These cross-references guide you towards those kinds of comparative questions and broader patterns.
So exploring one OEIS page really can be a starting point for a much wider exploration. You get the definition, the numbers, the history, the computation, and pointers to related problems.
Precisely. It gives you the sequence, the how, computation theory via references, the why, its place in combinatorics, and the where else, cross-references. Learning to read an OEIS page is learning to navigate a map of mathematical connections.
We've taken this deep dive into A000251, the count of diameter 6 trees. We went from a basic graph theory idea to seeing how it connects to classic papers, modern computing, and this whole network of related sequences in the OEIS.
It really is a nice example of how a specific counting problem can touch on so many aspects of mathematics and its history.
And how the OEIS captures all of that. So, as you, the listener, maybe explore the OEIS further, here's something to think about. We know A000251 counts these trees. But what else does the strict diameter 6 constraint force on the structure of those trees? Are they more likely to have certain numbers of branches or leaves?
And conversely, can we see properties in the sequence A000251 itself? Perhaps in how fast it grows, or if it satisfies some recurrence relation. Do those numerical properties somehow reflect the structural constraints of diameter-6 trees?
Those are great questions. And what about going further? What are the big challenges in counting trees with much larger diameters, say diameter 50 or 100? The methods must get pretty complex.
They certainly do. Enumeration problems often become computationally challenging very quickly. But the OEIS provides that essential starting point, the known data, and the links to the methods being used.
It lays the groundwork for those deeper questions. Well, thanks for guiding us through A000251.
My pleasure. It's a fascinating corner of the mathematical world.